Hello. In Unit 5, Ionic and Covalent Compounds, a typical problem is if given a set of percent composition data for a particular compound, can you figure out the empirical formula and the molecular formula? And I have a problem set up already. And that problem has to deal with a compound called estradiol. Estradiol is a molecule that is part of the estrogen hormone class. It is made up of carbon, hydrogen, and oxygen. Combustion analysis gave the following data. What combustion analysis does is that it burns a compound and it gives you the percent of each element. Oh, actually here I don't give you the percent of hydrogen. We'll figure out how to deal with that in just a bit. So with this composition analysis data, it says that the percent carbon by mass is 79.36%. When they say percent by mass, what you want to think of is if you have 100 grams of the estradiol, 79.36 grams of that is carbon. And then if you have 100 grams of estradiol, 11.75 grams of that is oxygen. Now it doesn't matter. It's doubtful that they burned or combust 100 grams of estradiol, but whether you have one molecule or a mole of molecules, the percentages stay the same. Whether you have a milligram of the molecule or the compound or 100 grams of the compound, the percentages still stay the same. The problem here is that if the molar mass of estradiol is 272.42 grams per mole, what is the empirical formula? What is the molecular formula? And if you recall, the molecular formula, for instance, for hydrogen peroxide is H2O2, H2O2. But you can reduce it to lowest terms to HO, right? One atom of hydrogen, one atom of oxygen. That is the empirical formula of hydrogen peroxide, HO. Okay, how do we want to tackle this problem? We want to understand, again, the concept of what it means to have a data that's percent of an element by mass. And to make things simple, why don't we just pretend? Why don't we just pretend we have 100 grams of estradiol? What that means is that for carbon, I have 79.36 grams of carbon, and I really need to figure out, question mark, C blank, H blank, O blank. I need the subscripts of each element for the empirical formula and the molecular formula. Well, these are, you can think of it as ratios, molar ratios of the three elements. What I'm saying is, let's get the moles. If I really do have 79.36 grams of carbon, how many moles is that? So we are going to multiply by what? We got to get rid of the grams and have moles on top. We're going to pick up the molar mass of an atom of carbon, 0.011. That goes on the bottom, right? 1 mole, 12.011. You see why I took the inverse of the molar mass of carbon? Because I want to get rid of that. Now let's see if we get a whole number. That'd be great if we got a whole number. We could automatically put it there. 79.36 divided by 12.011. 6.607. Let's give quite a number of significant figures. I don't want to round really until the very end. I think that's enough. Grams, no. Oof, what is going on? Moles of carbon. Hydrogen. Well, I don't give us, or the combustion analysis does not give us the percent by mass of hydrogen, but all we need to do is take 100% minus 79.36 minus 11.75. So the leftover is the amount of hydrogen, percent hydrogen. 100 minus 79.36 minus 11.75. 8.89, that is a percentage. Okay, so those three percentages should equal to 100 because I did say that estradiol only has those elements, carbon, hydrogen, and oxygen. Okay, 8.89%. But again, we're going to pretend that we have 100 grams. What that means is that 8.89 grams of that is hydrogen. And now, since I've done this before with carbon, I know that I have to divide by the molar mass of hydrogen, 1.008 grams, again to give us moles. 8.89 divided by 1.008. My goodness. This is going to be interesting. I got 8.819 moles. I'm a little worried. They're not multiples of each other. Let me just double check real quick. 79.36 divided by 12.011. Okay, 6.607. 8.89 divided by 1.008. All right. Those are the numbers I got. Let's keep going. Oxygen. Oxygen is 11.75%. 11.75 grams times 1 mole divided by molar mass of oxygen, 15.999 grams. 11.75 divided by 15.999. Interesting. Okay, we'll just go with the data. 0.734 moles. Okay. What do we have? These are the ratios, the molar ratios of the three atoms. We have carbon, 6.607, hydrogen, 8.819, oxygen, 0.734. But obviously, you've never seen a molecular formula that has decimals. They should be whole numbers, right? In a molecule, you have whole atoms making up that molecule. The trick is next to divide by the smallest number. You know what that accomplishes? It makes this oxygen 1. It makes this oxygen 1. And then we're hoping that when we divide it by the smallest number, each of these, we have whole numbers. That may be true for this case. It may not be true. We just have to try. So for carbon, if I take 6.606, 6.607 divided by 0.734, oh, yeah, 9. Okay. And you're going to have to use some discretion because if it was 9.05, definitely you could round that to 9. If it's 9.1, maybe you could round that to 9. But if it's 9.25, no, you can't. I would write it as 9.25 and then keep going, try to find a multiple that makes all of those whole numbers. But right now I have 9.00. We're going to call that 9. Okay, remember the steps? 8.819 divided by, again, the smallest mole amount is 0.734. Okay, 12.01. Okay, so we're going to round that to 12. And then since we are dividing this, all of them by 0.734, we know that this is 1. That is the empirical formula. We cannot reduce this to lowest terms. And yes, these are all whole numbers. That's what you're trying to accomplish when you're trying to answer this first part. the empirical formula part. All are whole numbers. Now, what was that case where I said if this was 9.25, you should not round it, and maybe it's a little bit unlikely because it's such a large molecule, but if you had 9.25, for that to be a whole number, if you multiply it by 2, it's 18.5, so that's not a whole number. 9.25, most likely if that was what we got, we would multiply by 4. And then we would have to multiply all of them by 4 and hope that we get all whole numbers, and that is in its lowest form. Okay. All right. That is going to be my answer for the empirical formula. Formula, and circle it so the grader can find it. What about the molecular formula? Now, the molecular formula can be identical to the empirical formula if the molecular formula just happens to be expressed in the subscripts expressed in its lowest terms, right? Maybe this is estradiol, C9H12O. Oh, by the way, you don't have to put 1 there, and you shouldn't actually, just put O, okay? So what's the strategy here? You're going to find the mass, and we could say the molar mass of this empirical formula, okay? Because we did say that the molar mass of the molecule itself is 272.42. So if this weighs 272.42 grams per mole, we're done. That is the molecular formula. All right. So the molecular, I shouldn't say molecular, I should say the molar mass, right? The molar mass of C9H12O is. I'm going to do this on the calculator. I'm not going to write it down. For me, or for my class, if students write this and then calculate without writing down how they got it, that's perfectly fine. I know what they're doing. They're doing 9 times 12.011 plus 12 for hydrogen times 1.008 plus oxygen on my periodic table is 15.999. And yes, if my students just give me this number, then that's perfectly fine. I don't want to round just yet, okay? Now, what do you notice about that number, 136.194? It is not 272.42. It's actually half. You know what that means? That I would have to multiply each of these by 2 to get to 272.42. Let's double check that. Times 2. See, 272, again, you want to have some discretion. That's close enough to the molar mass, and hence the molecular formula would be C18H24O2. Okay, but that was easy to see actually, that this was about half the amount of that. What you really want to do to show the math is you want to take the molecular, I keep wanting to say molecular weight because that's what organic chemists say instead of molar mass. But let me use the term that most general chemistry students use. The molar mass of estradiol, the one that's given, is 272.42. You're going to divide that by the molar mass of the empirical formula. And we calculated that to be 136. 136.19, let's just use all the digits there. That's going to equal, let's literally do that calculation. It's not going to be perfect, okay? Supposedly this combustion data is real data from a real experiment. Okay, so it's not perfectly 2, but it's, for all intents and purposes, 2.00. That is what you have to multiply each of these subscripts by. Okay, so I don't know how I can do this. You take this empirical formula, you multiply it by 2, and our molecular formula is now C18. Let's do the math properly. H24O2. Molecular formula. Okay. If we zoom out, not much work in terms of calculation. Figure out the moles. See if you divide each of those numbers by the smallest number if you get whole numbers. In this case, we did. If not, then you might have to multiply by some factor to get them to be whole numbers. When you get the empirical formula, just find the molar mass of that, and you take the molar mass that's given usually, divided by the molar mass of the empirical formula that you just found. That is the factor by which you multiply each of those subscripts to get the weight up, right? Because we were short, right? We only got halfway to 272.42 grams per mole. Okay. I have a problem set up that you can do at home on your own. In this video, I'm not going to tell you the answer, but you can easily find the answer just by looking up empirical formula and molecular formula of the compound that I'm asking about in this take-home problem. Using the following percent composition data, what is the empirical formula, question mark, and the molecular formula, question mark, of the amino acid cysteine? Cysteine is an important amino acid for proteins to maintain their structure. And it looks like, whoa, it's made out of carbon, made out of hydrogen, oxygen, nitrogen, and sulfur. These are all percentages. And if I add those up, they should be close or exactly 100%. I'm giving you the molar mass, just like we gave the molar mass of estradiol. And yeah, go ahead, and now we have 5 elements to deal with. So you're going to find the moles of each of these and continue the steps that we use to solve, again, this problem here.